Good afternoon. My name is Adam Klett. I am the Director of Science at Kaizen Corporation, and today I'm in the Global SMT and Packaging booth in the IPC Apex show in sunny Anaheim, California. Today I am pleased to be joined by three subject matter experts from across the industry to talk about a subject that is near and dear to my heart, which is the cleaning of no-clean fluxes. Today we have with us Josh Huther, who is a Senior Staff Process Engineer at Plexus Corporation.
Hello.
We have Dr. Mike Bixenman, who works at Magnalytics. And we have Vladimir Sitko, who works at PBT Works.
Hello.
Thank you, gentlemen, for joining us here. So I want to kind of start off the discussion by setting a stage for why we have no cleans and kind of why they were developed in the first place. Can you kind of give us an idea of why no clean fluxes were developed in the first place and why we still have them today?
Sure, I'd be happy to answer that. When you go back almost 30 years ago, the Montreal Protocol was enacted where there was ozone-depleting materials that were being eliminated. At that point in time, there were rosin-based fluxes, and most all of those fluxes in Class 3 environments were cleaned in a vapor degreasing process. And so as they started to look at alternatives to these ozone-depleting solvents, there was a wide array of different cleaning materials that were designed at the time to clean where assemblies needed to be cleaned. But also, that was the introduction of the concept of leaving a benign residue onto the circuit assembly that did not need to be cleaned. And so that was the early evolution of the no-clean flux.
So then do we still see a need for no-clean fluxes today? Is that why they're still in use? Because, go ahead.
When you consider a no-clean flux, it's really a material set that is low in activity. You know, when we think about what causes failure on an electronic device, and what's driven a lot of failures is the pitch distance between the components. As it gets closer together, we were listening to that keynote today, and he's talking about 1 millimeter pitch. You start to think about how close those conductive paths are. Any type of ionic residue that can cause water to bridge a conductive path can lead to a leakage current and a dendrite. And so with these no-clean fluxes, they were designed to encapsulate the residues and be hydrophobic. So they didn't attract moisture. And all of these fluxes need activators. So one of the key areas as well is that how deliquescent is that activator? Will it cause that water to bridge that conductive path? So the whole design is trying to prevent an ionic residue, number one, and secondly, to be hydrophobic and to create a barrier so that moisture will not want to coalesce or form that transient film between the conductive paths.
That's a great point. I think it sounds almost like a misnomer because from what I understand, what you're saying is it's more like a low residue flux because there are plenty of people that do clean them. And if you consider, if you look at the J standards, for example, J standard 001 refers to no clean processes, but it doesn't ever specifically say no clean flux, nor does the J standard 004. It calls out other types of flux, but no clean flux is not specifically defined. Now, the cleaning handbook does mention no clean fluxes, but the J standards do not. Is that an accurate representation of
Well, all of these flux materials are classified. Whenever they, through the J standard 004, they give them classifications, and there are numerous solder pastes with the classification that would meet a no clean flux is an ROLO classification. And so a number of different materials can fit that classification, but it's those functional additives and the activators that are added to the flux that could pass that high level standard, but could be problematic. when they're left behind.
I think that really hits it. Because you don't have any flux that is guaranteed to be acceptable to not clean for all circumstances and all products. There isn't such a flux or a material set like that.
So Josh, as a user of these no clean materials, can you kind of walk us through your process of choosing a no clean flux and then deciding to go ahead and clean it?
Certainly. I think that when you look at a no clean flux, it's important to make sure that you understand what that residue actually does. So you first want to make sure that you're classifying the flux residues and any sorts of interactions that you have with that material. So you're looking to do SIR testing potentially, ion chromatography testing, even doing some Rose testing to understand what sort of extractable ions are there. So you have to qualify your materials first like that, but then you want to make sure before you actually use it that you qualify its effect on your product. You have to make sure that you're doing a test and leaving that residue and making sure that in a functional environment that material is still benign and you're not going to have issues with affecting RF signals or leakage currents or any sorts of material compatibility with adhesives or coatings.
Okay. So you mentioned the issues that you could potentially have. Can you maybe expound on that? Like what specifically what issues could happen, and how do you address those?
So again, typically if you're seeing issues related to electrical performance, so if you're seeing excessive leakage currents, or certainly if you're seeing any sort of corrosion or dendrite growth in the field, you want to make sure that your processing is right first of all, and that you're fully activating those fluxes. They're going through a reflow profile that is giving you fully driving off any sorts of solvents or different materials like that. And if you don't have that full activation, even a good no clean flux isn't going to be acceptable as a residue. But if you do see still those electrical issues after making sure that you have a good reflow profile and that flux is fully activated, you have to go and look at some sort of cleaning to remove that residue to address those concerns.
Okay, and just for the users out there, can you remind us what you mean by flux activation?
So that means that it is getting to the right temperature for the right length of time. So you're driving off solvents, so you're really getting that cross-linking matrix that happens in most no clean fluxes to fully happen, and you don't have unencapsulated flux residues, things like ionic salts or acids that are residual in there present.
So if I don't have complete activation, are the problems that one would see similar to those if I just didn't clean well?
They're similar.
The same key, the same.
Yeah, you'd still see the same symptoms. You'd see the
yeah.
the dendritic growth. You'd see potential corrosion products being there.
And Vladimir, from the side of manufacturing the machines, do you see the same kind of issues, and then how do you address them from the machine point of view?
Well, basically, cleaning no clean fluxes is the same like cleaning fluxes which intend to be cleaned. We don't distinguish especially category of no clean because anyway this is a commercial name. But what is most essential is the solubility of the resin with the choice of the cleaner. And the differences between well soluble and well cleanable and hardly cleanable flux might be, let's say, 1 to 10 comparing the energy or time spent to clean it. And today, when we come to bottom terminated components massively, the challenges are multiplying even. So if you have bad luck and your choice is hardly cleanable combination, then the washing time, which is the first process step, might take more than hours. And then your chemical compatibility of the components is suffering, and the result is never perfect. And our experience, if you clean, you have to clean 100% thoroughly, perfectly, without any visible residues and without any film residues which can cause ECM. later.
And that's a really good point. And I've heard, Mike, you've made presentations in the past with Vladimir about the dangers of partially cleaning. Can you maybe really quick tell us a little bit more about that?
Sure. You know, when you leave a flux residue outside, maybe a water-soluble residue would be a bit different, but, you know, these residues have what I call an oxygen barrier. They have a resin-based area that basically encapsulates, you know, your metal oxides, the other functional additives that haven't been outgassed, like what Josh was talking about. When you partially clean a residue, you're breaching the oxygen barrier. You're opening it up, and when you open it up, you now create a condition where, if moisture were to be present, if you're in a high humidity area, or you see changes in temperature and humidity where you get some condensation on a test card, well, then it's going to naturally absorb into a partially cleaned residue, which can actually hold that moisture, which could amplify a failure, you know, if one were to occur.
So it's very easy to see a partially clean flux on, for example, like an SIR an SIR test.
Well, in some cases, you know, when we run SIR tests, we always like to remove the component. We shear the component. We want to look at the visual side and compare it to the SIR side. With a lot of these no clean fluxes, you know, the cleaning process is one where it's kind of additive. So you know, the cleaning material is kind of cleaning layers. So, you know, some of these no clean fluxes, you know, the oxygen barrier can still be intact underneath that component, and you get good SIR values. If you have maybe a softer residue like a rosin residue, that then, you know, it has a tendency to turn more white, and it's easier for moisture to breach at. So there's a lot of material sets that come into play. One of the real strategies of the solder paste companies is to design these, you know, materials, resin materials or polymeric materials that, you know, leave a harder residue that's harder to breach. When that happens, it's harder to clean. So in some cases, if you don't fully clean it and it's left, you know, trapped underneath a low profile component, you could run it through SIR testing and still get a good SIR result. But it's, again, if there's you know, a portion of that lowers the relative humidity, that causes, you know, that moisture to get present, then you start to see the failures rapidly, very quickly.
Very interesting. So Vladimir, I wanted to go back. You made a comment about how there's a very strong correlation or a very strong connection between both the machine and the chemistry that's used. You work very closely with the chemistry providers to make sure that the solution that is provided to the final end customer, it works. Can you maybe expound a little bit upon that relationship and more about that?
Well, if you build a machine, then you have to learn a lot more things than the standard chemistry man, because this is a combination of the physics and hydrodynamics and the chemistry, indeed. From the nature, the most used type of the cleaners are microemulsion or water-based cleaners, which consist of two separate phases. Partially they are dissolved, about to 5-6%. They are dissolving in the water, and the rest forms emulsion. The surface tension is very different. It's more than 2 times smaller surface tension in the organic phase than in the water phase. And the one challenge which you have to overcome in the machine is to keep the mixture steady in the machine. It's not so easy. From experience, the fresh cleaner tends to separate much more quickly. If you load it with some percentage of the flux, the separation is not so intensive, but still is there. And if you don't have this totally mixed mixture, then from the principle of machine building, you sucked the mixture from the bottom of the tank and you don't suck the proper concentration. You might dose 25%, and in fact, on the nozzles, you might have even 20 or 18 or really not in single percentage difference if the machine is not properly designed.
Okay. Now, would you say that it's a fair statement that no clean fluxes are in general harder to clean than the other, like water-soluble fluxes and other types of fluxes?
I would like to ask kindly the manufacturers of the flux not to use in advertising the no clean, but better to state some features about the solubility with different cleaners. That would make the situation of the users much more easy. We have developed the quite dedicated test for solubility, dynamic test, with the very precise made glass boards with chips, and we can quantify the solubility, the combination. So we can sort up the type of the different fluxes with different cleaners. And if somebody tells me I have flux XA and the cleaner B, then we immediately can say, okay, you have a good luck or you have a bad luck, and you will swear during the cleaning. It's really very different situation.
That's a really good point. So I want to kind of take it over and talk to Josh a little bit about the tests that are done when you as a user clean a no-clean flux. How do you make sure that you have cleaned your board?
So, again, I think that you have to do a few different things. I think it's important, first of all, that you work on some sort of a coupon or a test vehicle, and you're talking really about, at a base level, are the materials, the flux materials and the cleaning materials, and your coating equipment or your cleaning equipment materials, are they all compatible? So I think you have to do that first, but that's usually done on a relatively easy to clean test vehicle, or maybe even like a B52 test coupon. I think really that next step that you have to do is you have to take that to your product, because a lot of times the challenges on specific products are a lot harder than what you'd see on those test coupons. You can have really low standoff devices, things like QFNs where your standoff is so low that you rely on the chemistry altering the surface tension of the water to be able to clean under them. And then if you have those components and they're shielded by other large components around them, that makes for a really extreme cleaning challenge that you might not get on a coupon. But to qualify it, again, you'd look at a test vehicle, so you do SIR on a B52 coupon. That's a great way to look at the actual activity of residues. A lot of times what you'll see is you'll also see visually. You mentioned visually. Sometimes that's the hardest test for a no clean flux residue is it visually present? That's harder to get than a passing SIR value. You can also look at two other things. You can look at ion chromatography, which is really good and indicative of what sorts of residues are left. Little bit misleading because often you're either looking at one spot or you're looking at the whole board, and there's different interpretations depending on which area you're looking at. And then you can also look at like a Rose testing from a process control standpoint, how much total extractable ionic content is in the residues I have.
Well, thank you. So, Mike, can you, from a testing perspective, like for like a test house like Magnalytics, from the IPC standards, can you kind of walk us through what it looks like to be able to provide that objective evidence that the IPC asks for?
Sure. So when you look at the IPC standard, it's in objective evidence, you're testing for acceptable levels of flux and other process residues. And so typically that testing first starts out with electrical testing, just like what Josh talked about. SIR testing, the benefit of SIR testing is that we're testing the distance between pad structures of opposite polarity, and we're putting it in a stress condition. We're putting it into a temperature, humidity, bias condition. So we're creating an electrical field. So the first part of qualifying to the J standard is, do you pass SIR testing? Are you passing under specific components? Today, where SIR testing has come from or migrated to is that it was originally started out with just a straight SIR comb pattern. People like Plexes developed test cards with different components with laminate dummies so that they could test underneath the body of the components. So part of where SIRs come from today is that more and more test vehicles are being designed that are truly representative of the product that's being built, so that you can get an accurate representation, because failure is not across the board. It's component specific and it's process specific. From the component standpoint, if you're on surface mount, it's your stablest process, but it's if you have such a low gap and you're not fully outgassing, you can leave a pliable residue that can attract moisture. But the real area that we see a lot of failures is the secondary process steps, whether it's selective soldering or manual rework. Everybody does that. And in those particular areas, if you're building to no clean, you could be spreading residues because you're not cleaning them. And so, that's where, in many respects, is there really ever a true no clean process? It's probably not, because, you're cleaning all throughout the process, even if you're building a no clean board. And so it really gets down to, understanding process conditions. So when we SIR test, the most value that we can give a customer is knowing all of their process conditions. We want to understand everything that they're doing. If they're cleaning, what are the cleaning parameters? What cleaning material are you using? What is your concentration? What's your temperature? If you're using soldering materials, what's your stack up? And what's your reflow conditions? If you know those conditions, and just like what Josh was saying, you can vary those conditions, you can also vary the result. So, part of this testing is really not to, part of it is to say, yes, I've got objective evidence that my process is good. But the real value in the testing is the collaborative approach of going back to the customer and having a discussion about what we found and what actually drove the problem and what you can do to correct the problem. Because it's all about process, and they're building a quality product in the first place. It's when you miss on the process condition is where you start to see the issues that arise.
That's a really good point. Did you have... Okay. So Josh, have you ever encountered a scenario where even though your cards have met the standards, that didn't meet other functional requirements and then you had to, I don't want to say make up your own or your own passing criteria, but does that question make sense? Have the standards ever let you down?
Oh, standards have let me down. I'll take that into part wash compatibility testing. That's a place that standards are really, I'll say, struggling to keep up. There's been some really good work that's been done recently, but typically when you look, and you're looking to a no-clean process where you're cleaning, so you're using a saponifier. That material that you're using is not what the old test methods used to validate that components could withstand. If you look at the old mill standard test method, I think that the solvents are like terpene, which is just not an effective solvent in saponifiers anymore. So you look at that standard and it might say, yes, this component is compatible with wash, and it passed this mill spec method, and then you run it through your wash and it just falls apart. I have seen that many times, and that's a real struggle for us. Like I said, I know there's I think it's 9505 as a new IPC standard that's looked at some improvements to that and some history around that, and that's better. But even then, you look at a lot of these components and the challenges with them, there isn't a good documented way to understand if a component is going to handle a wash unless you get it into your specific process with your materials, at your temperatures, at your saponifier concentrations, and prove out it's effective. Certainly, that's a real challenge.
Yeah. So we only have a few minutes left, and I wanted to end by talking a little bit about the consequences of not cleaning. Now, for those out there who run no clean fluxes and don't even understand why companies like Kaizen are in business. Like you clean your boards, you clean your fluxes. Can each of you kind of provide a short example of, what can happen in your world if you don't clean or you fail to clean properly? What are the consequences of not cleaning these no clean fluxes?
Not cleaning no clean flux, it will fail test. We have RF products that will fail test. We have high-end industrial products that will fail for leakage current. That happens all the time. If you have partially cleaned residues, to your point, you'll see corrosion. You can actually see field failures. And certainly you can see that with water-soluble residues if you leave them. That's actually worse if you leave those, but you do see that with no cleans as well if you don't understand your cleaning process and control that well.
So when I look at it, when you build a circuit assembly, if you want to build to a no-clean process, it's got to be extremely well controlled. But, when you're building an assembly, there's multiple soldering steps that take place. You got top side, bottom side, you have selective soldering, and almost invariably, there might be an issue. There might be something where you have to do some manual soldering. So each one of those handling processes is an additive process. So the hard part about being truly no clean is that it's very challenging to have a process that's always in control. And anytime it's out of control, cleaning has to come into play.
Vladimir, did you have a comment?
Well, we have a lot of customers, they clean, but also we meet customers, they say we don't need to clean. But they should consider, first, if they start cleaning, they cleaned everything on the board. Also the dirt which comes during the production. Mechanical parts, very, very small FODs. And the other point is how long the assembly should live. Because you can make first failures which you keep by tests in the factory. If your reflow profile is not optimal, the activators are not bent out, and you see it. You see it on the SIR, you see it with chemistry. But if everything is okay, it does not mean it will be okay in half year when meeting different harsh conditions, or in 2 years. It very much depends on the reliability and on the lifetime you project for the component. And this is not always same, and many people don't realize the challenges what the product will meet in its life.
Yeah, those are really good points. Well, unfortunately, we're out of time. I think that we could probably talk for hours on this topic, but I'd like to end by saying thank you to my panelists here for giving us your time and your insight into the cleaning of no clean fluxes. And for those of you tuned in online, I'd thank you for tuning in. We really appreciate it. And we're going to end this with a short PSA. Thank you.
Every year, thousands of innocent circuit boards are manufactured without proper cleaning procedures. Used in high reliability applications like EVs, airplanes, and communication equipment, this oversight leads to a silent, creeping danger: dendrites, which grow over time and threaten their functionality. Hi, I'm Dr. Adam. For just the price of a small coffee, you too can make a difference. You can help stop the spread of dendrites, the tiny invaders that threaten the lives of circuit boards everywhere. Your support helps provide essential tools like cleaning solvents, fixtures, and clean storage bags to rescue circuit boards in need. Together, we can give these boards a second chance at life. Don't let another circuit board suffer in silence. Call the number on your screen or visit our website. For just a few cents per board, you can join the fight against dendrites, because every circuit deserves to shine.
Kaizen is the leading global supplier of award-winning cleaning chemistries for electronics assembly operations. Whether you are cleaning stencils or final assemblies, our global team of cleaning experts is there to help you succeed. Want to know more? Stop by our booth or visit kaizen.com.
From micro dispensing there is one product line that is proven and trusted by manufacturers in semiconductor packaging, electronics assembly, medical device, and electromechanical assembly the world over. DL Technology, superior pumps and needles for the finer things in life.
Video proudly sponsored by Kil Young Technology.